The AMGM inequality states that, given a sequence of numbers, the arithmetic mean is greater than or equal to the geometric mean. And today we are going to prove that using calculus. So first of all, arithmetic mean is defined such that the sum of individual items in the sequence is equal to n times the arithmetic mean. And we are going to use a subscript n to indicate that we have n numbers in the sequence. On the other hand, the geometric mean is defined such that the product of individual items is equal to the geometric mean raised to the nth power. And we also want to denote the number of items with the subscript n. As we go along the proof, we need to know how to find the global minimum of a function f of x. So the way we do is simply by setting the derivative of f to be 0, and basically hope that the graph look like this, where here will be our minimum point. So the function that we are going to consider is the following function in blue, which is a complex fraction. As we just mentioned, we need to find the first derivative of this function. But before differentiating this, we can make a little bit simplification or rewrite the expression. So first of all, you see we have the sum of the sequence where we have n items in total. So we can replace that by n times the arithmetic mean of n numbers, adding x, and we are going to bring the numerator here further down to this place. Now another simplification is that you see the product of a sequence in the denominator. So we can rewrite that as the geometric mean raised to the nth power. But because we have the product under this radical sign, the overall power will become n over n plus 1. And of course, we have to multiply that by x to the power 1 over n plus 1. Now we can realize that this function is in terms of x, which means that we actually have some constant that we can replace with some single variable, as we say. So for example, we can let b to be the constant here, so n times the arithmetic mean, and c equals to the constant right in front in the denominator, so n plus 1 times the geometric mean raised to this power. So we don't have to differentiate that because they are just constants. So we can then rewrite the function in terms of b and c, and also we can split this fraction, if you notice here, so that the differentiation will be easier. So after splitting up the fraction, it will become b over c times x to the negative 1 over n plus 1 power, because we are going to bring the x term to the top, and also adding 1 over c. This time we can simply do a subtraction of the powers, so x to the power n over n plus 1 in this case. So now the function is more simplified, and we can then differentiate this function. So f prime of x, we simply need to use the power rule to drag the power down and subtract 1 from the original power. and we add it with the second term, so 1 over c, dragging the power down, and then subtract 1 from the original power. In this case, the new power will become a negative 1 over n plus 1. And the next step is to set this derivative to be 0 and find out the corresponding x value. So we can actually cancel out a bunch of stuff, for example, the numerator here. And also this term, the whole term can be cancelled out. We don't want that to be 0. And we will be left with negative b over x plus n equals to 0. And equivalently, we have x being equal to b over n. And if you look back to our definition here, if you divide both sides by n, we get that x is actually the arithmetic mean. So actually, this tells us that the critical point appears when x is equal to the arithmetic mean. So we would also like to find out the corresponding value of the function. So the value, when you plug it, plugs the arithmetic mean into maybe here. Okay, both x's here. You see the numerator can then be factorized, so we can factor out the am, and what will be left will be the n plus 1, which cancels exactly with that in the denominator. So the numerator is simply the arithmetic mean. Now the denominator, we still have the gm term here, and also when you plug in arithmetic mean to the x value, we have another term of the arithmetic mean. We can also simplify that because we can just subtract the powers of the am term. So it becomes am to the n over n plus 1 over gm also to the very same power. So this is our critical point, but we want to show that it is in fact a global minimum point. So what we can do is to consider the points just in the neighbor of this point. So if x is greater than the am, so we have the derivative. If you plug in a larger number here, you are subtracting less from n. So in fact, the derivative will be positive. And similarly, if you consider a point an x value smaller than am, if you plug in here a smaller number, you are subtracting more from n. So in fact, the derivative will become negative. So actually, from these two properties, you can know that the graph will look exactly like this. So if you're on the right hand side of our critical point, you have an increasing slope, and on the left hand side, you have a decreasing slope. So this makes a global minimum point. So we can draw the conclusion that this value is the global minimum of f of x. And by definition, it means that f of x is greater than or equal to f of am for all x. To utilize this result, we have to pick some values of x to be plugged in into our new inequality that we just found out. So how can we pick an x value smartly? Well, if you look at our original function, you should realize that the whole numerator looks very similar to the arithmetic mean when there are n plus 1 items. And the denominator also looks very similar to the geometric mean when there are n plus 1 items. So in fact, if you observe closely, we can plug in an extra term into our original sequence. Or in another word, it is a sub n plus 1. So if you put a sub n plus 1 into our function, of course this will be greater than the global minimum value. And in fact, the function, as I've just explained, is exactly the arithmetic mean when there are n plus 1 numbers over the geometric mean when there are n plus 1 numbers. This is greater than or equal to the function, the global minimum point of the function. We just found that it should be this ratio of am and gm. But if you notice more carefully, we can also pull out the power and bring it to the outside. And naturally, we can raise both sides to the n plus 1 power. So we now have a very special inequality that describes the ratio of am and gm and their power. Now this is going to be important, and if you have done enough mathematics, you may realize that, oh sorry, this should be an inequality sign, okay? So you may realize that this looks very similar to a step in induction. So a typical proof by induction is some equation relating the case for n and the case for n plus 1. So if that is the case, we can in fact set up a hypothesis or a proposition P of n, or maybe P of t. We suggest that am over gm when there are t items, so raised to the tth power, is greater than or equal to 1 for all natural numbers t. So if we want to proceed the induction, we first need to consider the case when t is 1. So the left-hand side of the inequality becomes, so because we have only one term, the arithmetic mean and the geometric mean are both just the term itself. And you raise that to the first power. Of course, this gives you 1, which is the equality of P of t. So this is the case where equality holds. And notice we have just proven that this ratio satisfies another inequality. And in fact, this is already the last step of the proof, which is by induction, our original hypothesis is actually true. Because if you consider this very special inequality, it is suggesting that when you have an extra term in the sequence and the power also increases by 1, the ratio is just going to stays the same, either stays the same or increase. And if you do this, this is actually, it's very obvious that we have another hidden inequality, which is that it will be greater than the case when n is 1, right? So very naturally, we come to the conclusion. And the last step is very simple. You just need to raise both sides to the power 1 over t and move the term gm to the right hand side. Then you will get this result. And the t is no longer important because, well, it simply means that no matter how many terms you have in the sequence, this inequality must hold. And this is our proof by induction and using calculus very smartly.